Now we'll see the amplitude demodulator. Now in that amplitude demodulator, now this is a square law demodulator. Okay. Now before that we already covered the amplitude modulator, which is nothing but square law modulator. Now the same exactly the reverse operation of that square law modulator is nothing but the square law demodulator. Okay. But what is the input to the demodulator? The input to the demodulator is nothing but an AM signal, right? Now see here, this is an amplitude modulated signal as the input to the demodulator. Now this is applied to square law device. This is the square law device. Now square law device will producing the nonlinear relation. Now what is a nonlinear relation? You know that, okay? Now let us assume this is V naught. So first of all, what is S of t? Now the AM signal input to the square law device is an AM signal. You know the AM signal, which is nothing but AC cos 2 pi FCT plus AC KA m of t into cos 2 pi FCT. Okay, this is an AM signal which is input to the square law demodulator. So what is the square law equation? V naught. Now this is nothing but output of the square law device V naught, which is equal to A naught into S of t plus A1 into SS square of t. This is the square law device characteristics, right? Now nonlinear relation. So can I substitute here? Yes, you can substitute. Now which is nothing but V naught, which is equal to A naught into S of t. What is S of t? S of t is nothing but AM signal. Now which is AC cos 2 pi FCT plus AC KA m of t into cos 2 pi FCT. Now plus A1 into SS square of t. SS square of t is nothing but this is AC cos 2 pi FCT plus AC KA m of t into cos 2 pi FCT whole square. Now see here. Now I just expand those equations directly. Now the output of the square law device V naught, which is equal to A naught into AC cos 2 pi FCT plus A naught into AC KA m of t into cos 2 pi FCT plus A1 plus A1 AC cos 2 pi FCT plus A1. Now this is A plus B whole square. Therefore this is AC square cos square. Next B square, AC square KA square m square of t into cos square 2 pi FCT plus 2AB plus A1 into AC square KA m of t into cos square 2 pi FCT. Now this is the square law device output. Now what we are expected the output of the square law demodulator? We are expected the output of the square law demodulator is a message signal, right? So we want a message signal. Therefore this output of the square law device is passing through a low pass filter. This is passed through a low pass filter, and you design in such a way that the gain versus frequency characteristics this is the gain versus frequency characteristic of a low pass filter. Now, what is the frequency of this signal? The frequency of this signal is Fc, which is not allowed by low pass filter. The frequency of this term is Fc plus Fm or Fc minus Fm is not allowed. The frequency of this term is 2Fc, which is also not allowed. Now, the frequency of this term is 2Fc plus Fm, 2Fc minus Fm. This is 2Fc plus 2Fm, 2Fc plus or minus Fm. So, I can write the term like this. A1 AC square Ka m of t cos square theta can be written as 1 plus cos 2 theta by 2 plus A1 AC square Ka m of t by 2 into cos 2 pi into 2Fc t. Now here again this is 2Fc plus or minus 2Fm, which is not allowed. But what happened here? Here this is 2Fc plus or minus Fm, which is also not allowed. So only the output of the square law device is, now finally the output of square law demodulator, output of the square law demodulator or output of low pass filter, we call it as output of low pass filter. The output of low pass filter is A1 AC square Ka by 2 into m of t. Okay, this scaling is not a big task, so you can eliminate these scaling factors also. So by this low pass filter is passing through an amplifier circuit. This low pass filter is passing through an amplifier circuit, now whose gain, which is 2 by A1 AC square K. Now this low pass filter is passing through an amplifier whose gain is that one, then this is cancelled. Now the output of square law demodulator is finally, the output of the square law demodulator is 2A1 AC1 cancel, which is equal to m of t, which is a message signal. Clear or not? So the output of this square law demodulator is a message signal. So the square law demodulator is successfully get back the original message signal from the modulated signal as a input. Okay, this is the modulated signal as a AM demodulator input, and you can get back the original message signal. Okay, now first you note down this, and after that we will see the limitations of this particular square law demodulator. Square law demodulator limitations of square law demodulator. Now see here. Now after doing this square law demodulation process, now you just see here, you can easily understand. I remove all these things because this low pass filter will eliminate all these components. Okay. Now see here. Now here this term also I can divide into two parts. Cos square theta can be written as 1 plus cos 2 theta by 2. Therefore, A1 AC square Ka square into m square of t by 2 plus A1 AC square Ka square m square of t by 2 into cos 2 pi into 2fc into t. Now this is 2fc plus fm 2fc minus fm, which is not allowed by the low pass filter, is clear. This is also 2fc plus 2fm 2fc minus 2fm, which is not allowed by our low pass filter. M square is also not available, but why you are considering this? Now see here. Now you just concentrate here. This is the gain versus frequency. This is the gain versus frequency characteristics of a low pass filter. See here. Fn, okay, or omega, okay. This is omega is the highest frequency of the message signal, or Fn is the frequency of the message signal. So now see here. Now what is the purpose of this low pass filter? The low pass filter purpose is to allow the low frequency information signal, right? Now, right. Now my low pass filter is designed for the purpose of allowing a message signal of frequency omega. Now this is the low pass filter. Now this is the low pass filter. This is the pass band of the low pass filter, right? Now this is a signal which is a message signal, right, of frequency FM. For allowing this particular signal component, I am designing a low pass filter. But now if you see here, this is FM. What about this? The signal is squared, therefore this is nothing but 2fm or 2 omega. This is omega, this is 2 omega. If you observe here, this is minus 2 omega. This is 2 omega. Now this is because of m of t, and this is because of m square of t. But if you observe or not, now unfortunately this is my original message signal, this is my original message signal, but within this pass band this distorted signal is also present. This is unwanted signal. Am I not? This is the distorted signal. Now where is this distorted component? Now this distorted component, this unwanted component is coming because of m square of t. This is coming because of m square of t. So any signal other than the wanted signal, which is called as a noise signal, right? Now therefore, now this is the wanted signal, this is the original signal, this is the signal, or this is the wanted one. Now this is the unwanted signal, this is unwanted signal. This unwanted signal is nothing but a noise signal or a distorted signal. Now any signal which is other than the wanted signal is called as a noise signal or a distorted signal. Now, what is the signal to noise ratio? Now, see here, this is a signal, that is a noise. Therefore, then the signal to noise ratio wanted to distorted signal ratio is now A1 AC square Ka m of t by 2 by A1 AC square Ka square m square of t by 2. Now this 2 to cancel, A1 AC square cancel. Now here already 2 term is there, scaling of 2 is here, therefore this is not there. Cos of square theta is 1 plus cos 2 theta by 2 and this 2 is cancelled. So therefore now this is the case here. Now the signal to noise ratio or wanted to distortion ratio is 2 by A1 AC square cancel. Now this is Ka into m of, right? Now this is the signal to noise ratio. Sir, what we can understand with this? Okay, now by using this signal to noise ratio, now we can find anything. Yes, we can find anything, and we can identify the limitations also. Now, first you note down this, you can understand. Now this is the signal to noise ratio. The signal to noise ratio, which is nothing but 2 by Ka into m of t. Now this is the maximum value, Ka into m of t. This is the maximum value, and this is signal to noise ratio is minimum. Now this is the signal to noise ratio minimum value. The signal to noise ratio minimum value, which is nothing but, now what is the maximum value? The maximum value of Ka into m of t is Am cos 2 pi Fm into t. Now this is nothing but 2 by Ka Am. The maximum value of cos is 1. Now which is nothing but 2 by Ka into Am is nothing but modulation index mu. Mu equal to Ka into Am. So what we can understand here now, for a best system, signal to noise ratio should be as high as possible. We know that, as high as possible. So now you see here, the signal to noise ratio should be as high as possible. Now if mu equal to 10, now what happened to the signal to noise ratio? The signal to noise ratio, which is equal to 2 by 10, which is equal to 0.2. Okay, if the signal to noise ratio, if modulation index mu equal to 0.1, now what is the signal to noise ratio? The signal to noise ratio, which is equal to 2 by 0.1, which is equal to 20. Now, can you prefer a system of signal to noise ratio 0.2 or can you prefer a system of signal to noise ratio 20? Now we always prefer such kind of signal to noise ratio. We never prefer this kind of signal to noise ratio. What we can understand? So in order to improve the signal to noise ratios, the modulation index should be as low as possible, such that produces a better signal to noise ratios. That is the reason why practically the modulation index should be boundaries are less. What should be the boundary we are already set for modulation index? Is greater than 0 and less than or equal to 1. Okay. So why it is 1? What happened? 2, 3, 10, how? What happened? If modulation index should be the higher values, then the signal to noise ratio is less. Noise effect is more. Noise is dominating. So signal reconstruction is not possible. Demodulation is also not possible. Okay. So that is the reason why the modulation index should be the smaller values, signal to noise ratio should be the better values, such that there is a chance of demodulation process will make it easy. Okay. So this is the another advantages of the this is another reason behind why modulation index should be smaller. Okay. So what is the limitation of this square law demodulator? The limitation of square law demodulator is nothing but here the square law demodulator is preferable. The square law demodulator is preferable when modulation index is less than or equal to 0.2. Why? Because when modulation index is less than or equal to 0.2, then only it will produces a good signal to noise ratios. When it will produce a good and better signal to noise ratios, then the demodulation process will make it simple. Okay. So that is the disadvantages, sorry, not disadvantage, limitation of a square law demodulator. Okay. Now this is a story behind the square law demodulator. No doubt.